Hi everyone. Today we're presenting our work on performing real-time vision tasks on a high degree of freedom robot arm. As an overview, we investigated 3 vision tasks with 2 robot control methods. The 3 vision tasks are taking a stable panorama, detecting objects in real time, and tracking objects in real time. We also compared the effectiveness of 2 different robot control methods. The first method is to manually control the robot with an input device. We used 6 different axes on an Xbox game controller to map the position goal and the rotation goal. The second method is to write a script to fully automate the robot motion. The significance of our work is to explore the gap between computer vision algorithms and the real-world robotics applications. A real robot was not accessible to us due to the COVID-19 pandemic, so we carried out our implementation and experiments in a simulated environment. So, all the tasks in this work were tested on a robot arm with 7 degrees of freedom in a simulated scene. We chose to work on a high degree of freedom robot because it has a wider range of capabilities, such as spoon feeding, garbage classification, and heart surgery. For a robot, the ability to see and understand the world around it will be extremely useful. We used a motion planning framework called RelaxedIK to calculate the motion of the robot arm. This is an overview of our general pipeline of testing a vision task. The robot arm uses a vision sensor attached to its end effector to capture the environment information. Then, the robot platform communicates with the Vision API in real time for image processing tasks. Our first vision task is to take a stable panorama. OpenCV is a computer vision library. It has a built-in image stitcher which is well modularized and easy to use, so we directly applied it to stitch images captured by the robot. In the simulation, we programmed the robot arm to rotate at a fixed speed autonomously to capture a stable 180-degree panorama. Here is the montage of the frames captured by the robot arm, and this is the panorama after stitching. We also asked some testers without prior experience to control the robot arm to take panoramas with an Xbox controller. In order to test how intuitive this control method is, we did not provide any instructions such as the function of each button on the controller. It takes them about 5 minutes to learn the controls and take a stable panorama as the one in this slide. When some field robots explore unknown environments, it is useful to take a panorama of their surroundings to gather useful information. Our second task is to detect objects in near real time. Our first attempt is based on PyTorch and torch vision. Mask RCN is a model that predicts both the bounding boxes and the class scores for potential objects in the image. At first, we used a pre-trained Mask RCN model on the COCO dataset. Each frame captured by the camera is processed by the model for object detection. With only CPU, the latency for processing a single 50 kilobyte image is around 4 seconds, which is pretty bad for our goal of real-time detection, where we expected millisecond level turnaround time. With the goal of improving the performance in mind, we looked into other possible frameworks. The first modification we made is to switch to Detectron 2, a state-of-the-art object detection framework by Facebook Research. Detectron 2 is powered by PyTorch, and it has a wider range of features and a faster speed. After changing the framework, the latency is still pretty high on CPUs, so we looked into using GPUs. We did some benchmark experiments on Microsoft Azure and found that these 2 modifications combined resulted in a 200-time performance increase with a final latency of 16 milliseconds, which is equivalent to 62 frames per second. These benchmarks proved the viability for our implementation to be used in real time. The state-of-the-art real-time object detection method on a Nao robot has about 0.1 second turnaround time with a single GPU. It has close performance to our method, and the variance is caused by image size, GPU specifications, etc. Since we could not install the robotics software on the Azure remote machine, we did our implementation on CPU-only machines, which led to about 2-second latency. Here is a demo showing our implementation of the object detection functionality. Since the provided meshes in the simulation software have a relatively small number of polygons, and our model is trained based on real-world pictures, it fails to detect some objects in the experiment, such as the poorly made human model. Therefore, we expect this method to work better in a real-world setting than in a simulator. Our third task is to track moving objects in real time. First, we use the OpenCV implementation of the mean shift algorithm mentioned in class. It is a histogram-based tracking algorithm. There is one major drawback though. The size and the rotation of the tracking window are fixed. To resolve this, we switch to camshift, an algorithm based on mean shift that updates the size and the rotation of the window upon convergence. We use the Xbox game controller to control the robot in this demo. The tracking window size is constantly changing to fit the human figure, and as you can see, our method is robust to changes in orientation and scale. Our conclusion is that our implementation of the motion planning framework of high degree of freedom robot arms works well with computer vision tasks. Different control methods works well for each vision task, but fully autonomous robots might be more useful to carry out real-world tasks. Here is a list of future directions of our work. For Task 2, Object Detection, the first improvement is to integrate GPUs to speed up our real-time detection. Also, some testing in real-world settings should be carried out. For Task 3, Object Tracking, the camera should follow the object being tracked automatically. Also, the robustness to changes in scale and orientation can be improved. For more information, please visit our website by scanning the QR code. Thank you for your time, and we'll be happy to take questions.